So today's class will go over body plots. So the objective here is to learn how to sketch body plots. Now, what are body plots? Body plots are one way for us to graph um, frequency analysis, um, to graph frequency response of a system. There you go. So that we can perform a frequency analysis. So this is just one way to do it. It's a most common way of how people do frequency analysis is by looking at frequency response plot. And in this case, that one frequency plot is called body plots, right? And body plots are not the only way to do it. Yeah, in the follow-up class, in the control systems class, you learn more or different ways of plotting, frequency response. But again, the most common way that's being used um, by engineers these days are body plots for frequency response analysis, right? So here is the block diagram of our system, right? You have input x of t, output y of t. So the system itself is represented by h of s. That's the transfer function. Remember the transfer function that we talked about on Monday? So that system is represented by the transfer function, and then we excite the system with this signal x of t, and the system outputs y of t, right? So the transfer function itself is going to be the ratio of output over input, y over x, right? So that is what h of s is, right? And as I said earlier, body plots are standard method of plotting magnitude and phase. The reason why it's plural, plots, there are two of them, because one of the plots, you can see the variation of the magnitude of this transfer function with respect to frequency, whereas another plot, the other plot, shows the variation of phase angle as you vary the frequency, right? So both plots use a logarithmic scale for the x-axis. So the x-axis of the plot, these are log scale, not linear scale. We'll talk more about why we use log scale. And then the frequency itself is in radians per second. So the unit for the frequency, usually we use omega or radian per second. The phase is plotted on linear scale in degrees, whereas the magnitude is plotted on linear scale in decibels, right? So remember two plots, right? Phase angles and gain. Phase angles of h of s and the gain of h of s. So the gain on the y-axis, we plot it in terms of the decibels, right? Not linear gain, but decibels. Now decibels is defined mathematically to be 20 times log 10 base 10 of the gain, right there. Okay. And so you'll see later on that this actually has some benefits. Okay. And then the phase angle itself, it's plotted on the y-axis using the angle. So the unit is degree, right? Okay. So again, it consists of two plots, both of which have a logarithm of frequency on x-axis, the magnitude plot, and the phase angle plot, right? And the plots can be used to interpret how the input affects the output in both magnitude and phase over frequency. Right. And then later in a follow-up class, if you decide to take it, the plots will be used to assess stability of a system by measuring the phase and gain margin. So for this class, you're going to learn how to sketch the plots. But if you are interested in control systems, later on you could take a class and you learn how to make use of the plots, again to assess stability of the system. So here's more discussion on decibels. So you can see the equation for decibels is 20 times log of the actual gain. So X is the actual gain, but then you take a log of that, base 10, right? And then you multiply it by 20. So this is going to be base 10. So for example, so for this class, it is important for you to know how to do this. Okay, so this is the basic informed basic calculation of gains in body plots to convert from linear gain to decibels. So for short is dB right there, right? So the unit is dB. So dB stands for decibels. So for example, if the linear gain, let's say V out over V in, right, is equal to 1, then that's linear gain, right? So let's say input is 1 volt, output is 1 volt, right? That means the gain is 1, right? 1 over 1 is 1, but that's a linear gain, right? This is called linear gain. So in body plots, we instead of using linear gain, we use decibels. How? Convert it into decibels using this equation right here, right? So linear gain of 1 in decibels would be 20 log of base 10 of 1, right? Well, we know log of 1 is equal to 0, so it's going to be 0 dB, right? Okay. And then if you have gain of 10, right? If you have a gain of 10, that means that's a linear gain of 10. So for example, input voltage is 1, output voltage is 10 volts, like this. 1 volt against 10 volts. And what is the out of the in? That's 10 over 1, right? 10 volts over 1 volt. That's going to be 10. Gain of 10. That's linear gain, right? But then we need to convert it to decibels. How? Let's take 20 log of 10, right? Like this. So 20 log of 10 gives you, well, log of 10 base 10, right? Is equal to 1. So this is equal to 1. So 20 times 1 is equal to 20, right? And 20 dB for a gain of 10, and so on and so forth. Then you have, if you have a fraction, 0.1, then of course that's going to be 20 log of 0.1, again base 10, right? But 0.1 is the same as 10 to the minus 1, right? And then you learn that that's the same as minus 20 log of 10, right? Which is equal to minus 1. I'm sorry, minus 20. This is 1. So 1 times minus 20 gives you minus 20. And so on and so forth. Any questions so far? So make sure you know how to convert from linear gain to decibels. Okay. Any questions? No? All right. Okay, then here's an example of body plots. Right? This is from, what is it from? The plot below shows the frequency response of an idealized motor, data based on a simplified model of an actual motor. And here's an example of body plots, right? And typically we separate the two plots. So you have two different plots, frequency against amplitude in dB. Now you know what dB is, right? And then frequency against phase angle. But in this example, we combine both. We combine both amplitude and phase angles, as you can see. So there are two y-axes here. The one on the left, the y-axis shows the amplitude, right? Amplitude of the transfer function. And then on the right-hand side, that's the phase angle of the response, right? The outcome would be in. So the x-axis for both are always frequency, right? So here it turns out to be in hertz, doesn't have to be in radian per second, but typically in omega. But here is in hertz. So we can see how gain, right, the red one right here, varies with a frequency, right, as well as phase angle varies with the frequency, right? So from left to right is increasing, right? Frequency is increasing from left to right. And you can see the frequencies, the value is 10 hertz right here, and then 100 hertz right there. And you can see the log scale, right? Right there. That's the log scale. It's not linear scale. So from 10 to 100, you can see the, what do you call it? The scale is actually shorter, right? Imagine if it's a linear scale, then it takes more space to plot the data, right? But since this is a log scale, you can compress more data into a smaller space. That's one advantage of a log scale, right? So in case somebody asks why do we need log scale for body plots, so one advantage would be you can squeeze in, you can compress more data into bigger range of frequencies, right? Again, imagine if you use a linear plot from 10 to 1000 hertz, right? That's going to be a long plot, right? A long, what do you call it? Takes up a lot of space to plot the data. But again, here with log scale, takes up less space for plotting the data. Okay. Now here we can see just from these pictures, right? The explanation is down here below the graph, so you can read them yourself. But basically, what I explain here, right? All of these wordings or sentences or bullets is that I take a look at 3 different examples. The first one is at, was it below 10 hertz, around 5 hertz right here. So at 5 hertz, so that's 10, right? So this is 1, right here is 1 hertz. 1, 2, 3, 4, 5, right there, right? So you can see 5 is actually right here, 5 hertz. So below 5 hertz, right? Let's say over here. Let's say over here, right? You can see that the gain is 0 dB. The gain is at 0 dB, and the angle is at, the angle should be on the right axis. That's 0 degrees as well, right? So you can see that at, let's say at 2 hertz, let's just say, right? The gain is 0 dB, and the angle is 0 degrees, right? What does that mean? That means if you put in 1 volt at 5 hertz, sorry, at 2 hertz, sorry. If you put in 1 volt into the system, into this motor system, right? And then the motor will output 1 volt as well. Because 0 dB corresponds to a linear gain of 1. Remember that, right? 20 log of 1 is equal to 0 dB, right? So that 0 dB corresponds to V out over V in equals to 1. Right? So if you put in 1 volt, then you get 1 volt out. So the gain is equal to 1 or 0 dB. Right? So if you command the motor to move or to spin by, let's say, or to turn, I should say, to turn by, let's say, 90 degrees, then of course the motor will also turn by 90 degrees as the output. So 1-to-1 ratio, right? Okay, and then the 0 degrees right there, it means that the output does not follow, does not lag or lead the input, right? So it follows quickly, basically. So that's what it means, right? What we're doing now is frequency response analysis, basically, using body plots. And then that's the first example, right? At around 2 hertz. What about at around, let's say 10 hertz right here? Let's say that's 9 hertz right there, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 hertz, you can see the gain is actually above 0 dB. That's about, what is that? That's about 5 dB maybe, right there, right? So it's 5 dB, right? At around 9 hertz, it's about 5 dB. What is the angle on that? Well, we can take a look. The angle is right here. So it's about, what is that? Maybe about 30-ish, around 30, I don't know exactly. about, I would say 30-ish, like 30, 32 maybe, something like that. 32 degrees, right? And it's lagging because it's below zero. So that's minus, so it's minus 32 degrees. So what it means is that if you put in 1 volt, then the output is going to be more than 1 volt, right? Because the gain is positive, right? So how do we know the linear gain from the dB? Well, you go backward, right? If you convert from linear gain to dB, this is the equation, right? 20 log of the linear gain, right? That's in dB, gain in dB. What if you want to go the opposite? Then gain in linear gain, it should be, what is it? 10 of the gain in dB divided by 20, right? So in this case, if it's 5 dB, the actual gain would be 10 of 5 dB divided by 20, whatever that is, right? 10 over, what is that? 1 over 4, right? Like that. So that's the gain, right? That's um, the gain in linear, not in dB anymore, right? Okay, does it make sense? How about the phase angle? The phase angle at 9 hertz, if you put in the sine wave voltage at the input at 9 hertz, then the output will be lagging by about 32 degrees, let's say, right? If let's say this is 32 degrees, right? Okay, so that's lagging. The output, there is a delay on the output basically of 32 degrees. Okay, and then let's do one more. Let's say about uh, this one right here, 200 hertz, right? So let's say you put in a sine wave at 200 hertz into the motor system, right? Then what is the gain of the system? Well, in this case, it's not a gain, it's called attenuation. The signal gets reduced because the dB is negative. See that? It's a negative dB. Like, let's say about 25. Let's just say that's minus 25 dB. So at 200 hertz, right, the gain in dB is 25 dB, minus 25 dB. The angle is at what? What is the phase angle? That's 90 degrees, right? So 90 degrees minus 90 degrees. So you can tell from here, right, that by looking at the frequency response plot or body plot, you can now know that if you put in a sine wave at 200 hertz into the system, right, then the gain at the output would be a negative gain. It would be a fraction of what you're putting in, right? What is the fraction? Well, again, you go back from dB to the linear gain. So the linear gain would be 10 minus 25 over 20, right? That's the fractional gain that you get at 200 hertz. So you put in 1 hertz, then you get you put in 1 volt in, and you're getting out less than 1 volt. How much less? That much less, right there. Right? And then it's going to be lagging by 90 degrees. Right. Any questions so far? So those are 3 examples on how to read body plots, right? So I start from low frequency, mid frequency, and high frequency. Any questions? Right. If not, then let's move on. Now, as I said earlier, the objective of this uh, section for this class, right? Coming out of 212, um, you should know the basic of frequency response analysis, just like we did just now, right? The 3 examples we did earlier. You need to understand body plots, the units being used, right? And what goes on the axis, right? Again, the x-axis frequency, The y-axis would be phase angles and decibels, right? But then the next big objective for this class, for this section, would be for you to know how to sketch body plots, right? Now, of course, nowadays you can always use software, right, to sketch body plots, right, to graph body plots for you. But as an engineer, right, coming out of graduating from Cal Poly, you'll become an engineer. You need to know what goes on behind this graph. That way you understand not just how to read the graph, but how to design a system using the graph. Make sense? If you just need to read it, then you don't need to know how to learn how to sketch it. But if you want to understand what goes on behind the graph, that way you can design the system using the graph, then you need to understand how we can actually generate the plots. Okay, so that's the reason why we're going to go to this section on how to sketch body plots. All right, so please pay attention, because this, I believe this is the only class where you learn how to sketch body plot. Right, so what is the first step? Well, the first step, you need to know the transfer function, because when you generate body plots, you are plotting transfer function, right? You're plotting the transfer function based on the magnitude and gain. Keep in mind that transfer function is none other than a complex function. Okay. A complex function, just like a complex number, has what? Has magnitude and has phase angle, right? If you have a complex number, you can get a magnitude of the complex number and the phase angle of the complex number. Same thing with a complex function, right? So you start from knowing the transfer function. That's why at the beginning of the chapter, we learn how to derive transfer function, right? So that's the very first step, getting this right here. And on Wednesday, right, I mentioned that for transfer function, in general, you could form polynomials, right? Ratio of polynomials. Numerator, which is a polynomial, over denominator, which is another polynomial, right? That's what we talk about on Wednesday. Now, there are different ways on how to write polynomials, right? You can write the polynomials this way, or this is what you learn on Wednesday, right? That's how we can determine poles and zeros, right? Using this form. However, for body plots, so this is important, for body plots, to generate or to sketch body plots, you need to rewrite the body, not the body plot, you need to write the transfer function in what we call the standard form. And this is the standard form right here. I'm going to box that in right here. That's the standard form, right? So make sure, first of all, you know how to derive the transfer function. Once you derive the transfer function, then convert or rewrite the transfer function or write the transfer function in standard form. Always, right? Standard form. Is that clear? So derive the transfer function. Once you get the transfer function, then write it in standard form, which again, it looks like this. And we'll go through some examples, okay? So once you get, K1 here is a constant, right? K1 is the constant of the transfer function. Z1 is the zeros, right? Z1, Z2, Zn, those are the zeros of the transfer function. And P1, P2, and Pn, those are the poles of the transfer function, right? Okay, so again, standard form is used as the first step in sketching the body plot. Now, once you write it that way, then you can start sketching the body plot. But before I go there, let's look at this one example. Let's say that this is the transfer function that you're getting, right? You derive from a circuit this transfer function, and that's one way to write the transfer function. But this is not the way for you to write the transfer function for body plots, right? For body plots, you have to convert it into standard form. How? Well, first I'm going to what do you call it? factor out this polynomial. So I get, I get this new transfer. Another way to write transfer functions. Okay, you can see clearly those are the zeros and the poles, right? -3, -4, -1, -10. Those are the roots, right? But then again, for body plot, we want to get the standard form. How? Normalize the terms in parentheses. For example, you see s plus 3, right? S plus 3 right there, right? So s plus 3, you can normalize it. How? That's the same as 3 times s over 3 plus 1, isn't it? How about s plus 4? Same thing, right? S plus 4, that's the same as 4 times s divided by 4 plus 1, isn't it? That's why I have that term right there. This becomes that terms right here. And you see the 3 and the 4 right there. Good. Then I do the same thing. I did the same thing for the poles, right? For the one in the denominator. I do exactly the same thing for this and for this. See that? Right there and right there. Okay. And then at the end, I have these constants, right? All of these are constants, right? And I just combine them into one single constant. That's going to be 6 right there. And I have this s right there. Just leave it as s right there. Okay. So far, so good. So now, what I did was I convert, or not convert, but rewrite the transfer function into standard form right there. That's the first big step, right? Standard form. You can still see the zeros and poles, right? Right there, right there. Those are the zeros, those are the poles, right? You can still see them. Any questions? Now that you understand the first big step, right? Non-standard form to standard form, and let's look at how we can sketch body plots. Okay, straight line transformation, straight line approximation. Again, in general, a transfer function has the following form, right? And you have to again convert it into standard form, right? But let's say, as an example, I have this transfer function as an example. This is in general, right? But let's say, as an example, I have this form right here, where you have how many terms in this transfer function? I have 4 different terms: k1, s plus z1, s plus p1, right? Now, if you see s plus z1 right there on the denominator, this is what we call 0 not at the origin. If you see s plus 1, sorry, s plus p1 in the denominator, then we call that pole not at the origin. And if you see s right here, right, in the denominator, we call that pole at the origin. Why? Well, what is the root of f? That's equal to 0, isn't it? Right? That's why 0 is the origin. That's why if you see s by itself, that's on the denominator, that's pole at the origin. What if you have s by itself on the numerator? That's called 0 at the origin. So the following section, I'm going to go through explaining how to sketch each one of these terms. Right? How do you sketch a constant term? Right? K is a constant term. How do you sketch a constant term on body plots, on a gain plot? Right? This section is on magnitude, by the way.
Yeah.
Right? So this section is on magnitude. And then we'll continue on the phase angle on Monday. I don't think I can finish the magnitude today. We also continue the magnitude plot on Monday. But in this example, how do you plot a gain, right, on the magnitude plot of body plots? How do you sketch zero not at the origin? How do you sketch zero at the origin, and so on and so forth? Right? So you're going to learn how to sketch these, right? Now, from this example, right, I can rewrite it into standard form, which is right here, right? That's the standard form for that example. And again, I can combine the constants into just one single constant. I'm just going to call it K. Right? That's what I have right here. That K. Right? And then I would change S back to j omega, because remember S is equal to j omega, right? So now you can see that from this standard form, if you rewrite it, you get h of s, in this case h of j omega, equals to k times s over j omega over z1 plus 1, right? And then j omega over p1 plus 1, right? So I just replaced s with j omega, right? That's what I have right here. Okay. Any questions so far? Now, for body plots, remember we use dB. We don't use the actual gain, right? We use dB. So how do you use dB? You multiply the gain by 20 log of the gain, right? So if these are the gain, right, you change it to the gain function, then you have to take 20 log of this in order to get the gain plot. That's what I did right here, right, from here to here. So for the magnitude plot of the body plot, I have to take 20 log of the transfer function right there. Okay. Now, what happens if you take the 20 log of this function, of this whole thing? Well, this shows you another benefit of a log scale, of using the log scale. Right? Again, the objective here is for you to be able to draw, right, to sketch functions, right, to sketch the transfer function. For example, this. You're sketching this transfer function. Imagine if you're not using log scale. What are you going to do? Then you're going to do, you're going to plot each of the term, k, and there's another function right there, there's another function right there, and then another function right there. And then you're going to have to multiply the two functions and then divide by another function and then divide by another function, right? Can you imagine the difficulty in multiplying and dividing two functions? Let's say that you have the first function that looks like this, right? And then the second function that looks like this. I don't know, like just some random one like that, right? That's function, there you go. And then will that be difficult if you have to divide or multiply the two functions, right? The operation that you have to perform for the two functions in order to get the actual plot of the transfer function will be multiplying or divide, right? You see this? Multiply or divide. That will be a difficult operation to do, right? Would that be easier if I just add the two, right? This is the benefit of using log scale. Just watch. What happens after I take 20 log of this transfer function? What happens after I do this? After this, then it becomes this function right here, right? What's nice about this is that in log scale, multiplication becomes addition, and division becomes subtraction, right? And subtraction is none other than addition of the negative of the function, right? So minus, for example, f1 minus f2, that's the same as f1 plus minus f2, right? So it is still an addition of the negative of the function, right? So adding is an easier operation than multiplying or dividing. Yeah. And so now instead of multiplying and then dividing this function, you can just add the two. It's easier to add the two functions, right? Add point by point, right? It's easier to do those, right? And instead of multiply and divide. So that's the second big benefit of using log scale, is that now you can just add functions, right, to get you the entire transfer function plot, right? Again, you need to obtain the entire plot, right? So that is now can be easily obtained by adding four plots in this case. Does that make sense? Right. So then, if that is clear, then let's start with the easy one first, right? Then we can have this, how many different possible terms here. I can have constant term. I can have 0 at the origin. I can have 0 not at the origin. Right? I can have 4 at the origin. I can have 4 not at the origin, like this. So 1, 2, 3, 4, 5, 5 different terms. There's actually another term which is not covered in this class. I have the section later on, but I'm not going to cover it in this class. Right? But for now, these are the 5 different terms that you need to know how to sketch from this class. When we go one by one, okay? Any questions? Okay, let's take a look at the first one right here. Right, the game. Let's learn how to sketch a game in the magnitude plot of the body plot. Right. So the term is 20 log of k. Right, and k by itself is a constant, isn't it? So what is 20 log of a constant? Well, 20 log of a constant is another constant. Right. So the first one is 20 log of k. Like I said, k is a constant. So 20 log of, let's say, that constant is, let's say, 5. That's going to be a constant, isn't it? And how do you draw a constant in a semi-log paper like this? Like how do you do this here? That's going to be just a flat line. Right? It's going to be just a flat line, right? So that's what I have right here. That for a constant term as one of the terms in the transfer function, where you plot it is just going to be a flat line like that. Right? That's 20 log of k. Again, this is in dB, right? And here's in the as a frequency. Any questions? So that's the easy part. Is that clear? So the very first part, we're done with this, right? We're done with this first part. Now I know how to draw this part of the transfer function. That's just going to be a flat line, right? Now, what about this part first? Call at the origin. How do we draw that? Well, let's take a look right here. Actually, this one. So 20, the term is minus 20 log of j omega, isn't it? Yeah. Let me go back so you can see the term. So I have to go back here. See the term right there? Minus 20 log of j omega, right? Magnitude of j omega. That's the term we need to sketch, right? So let's go back here. Minus 20 log of j omega. First of all, this is the function we need to plot. I know from this function that when omega is equal to 1, what's going to happen? That's going to be minus 20 log of magnitude of j1. What is magnitude of j1? Anybody? What is the magnitude of j1 equal to? That's equal to 1, isn't it? Magnitude of j1 is equal to 1. That's an imaginary part of the complex number. Right? That's just going to be square root of 1 square. That's going to be just 1. So the magnitude of j1 is equal to 1. And what is log of 1? Well, log of 1 is equal to 0, isn't it? So therefore, at omega equals to 1, it turns out to be that we have 0 dB. So I have 1 point on the plot here, right? So that 1 point is right here. That for this function, when omega is equal to 1 radian per second, then we have 0 dB. This is the 0 dB cycle. Okay. Any question there? That's just 1 point though, okay? That's just a dot. Then how do we know the rest of the plot for this function? Well, I know that this function has this minus 20 in front of it, right? Just like y is equal to mx. What do you call that m? That's the slope, isn't it? Slope of x. Same thing here. Minus 20 is the slope of log of j omega. So therefore, I know that for the function minus 20 log of j omega, it has a slope of minus 20. Minus 20 what? Minus 20 dB per decade. Minus 20 dB per decade. So in 1 decade, 1 to 10, the function goes down by minus 20 dB. So from there, I get another point, and then I just connect the 2 points, and I have a straight line with a slope of minus 20 dB per decade. Is that clear? So that's it. That's how you plot a pole at the origin. But let me ask you this. What if I have, instead of, remember this is a pole at the origin, right? 1 over s, or 1 over j omega. What if I have 1 over s squared? How would this plot change if you have 1 over s squared? Anybody? Hmm? Any guess? If we have double poles instead of just 1 pole, how's that going to change? Well, that's going to be right here. Right? It's going to be, sorry, it's going to be
parabolic.
The slope, right? There's going to be 20 log of 1 over s squared, right? Remember s squared is j omega squared, right? J omega squared. So that's going to be 20 log of j omega, like this, right?
Doubled.
Yeah, so that's going to be
Negative 40.
Exactly. Like this. All right. So now it's going to change the slope. Instead of minus 20, now it's going to be minus 40. So this is going to be minus 40 dB per decade. So it's going to be steeper. In 1 decade, it's going to go down to minus 40. So it's going to be this straight line, steeper. What about if it's 1 over s cubed? What's going to be the slope? Any guess?
Negative 60.
There you go. Now you get the idea, right? So the more pole you have at the origin, the steeper the slope. Okay. Any questions? That will be it for today.